Compilation to native code looks like you're taking your high-level code, you are compiling it to a sequence of instructions that represent the instructions of a machine, even if that processor is a little bit abstract. RISC-V is there to paper over several processor semantics, but it is representing what the hardware would give you in terms of computation capability. It is representing details of that hardware. It is representing a very specific architecture. And then those real instructions, in some sense, are what you're proving over. If you are interpreting with an abstract machine, your control words are literally part of the language. And you are focusing on one part of the high-level program and saying, hey, that part of the high-level program, I can reduce it to something smaller. And when I say smaller, I mean literally syntactically smaller and simpler. And then I'm selecting another part of the program, and I am also reducing it to another piece that is smaller. Think of it like a compression function. Now, of course, if you're familiar with programming languages and the lambda calculus, what I'm doing is pushing symbols around. I'm reducing the stuff in question. I'm actually computing. But the core idea of abstract machines is the instructions do not correspond to any notion of processor or any notion of hardware. We don't, by definition, we're not made for that. Here's an example, the CEK machine. It fits in 5 lines and in 1 slide. Now you're going to tell me, okay, sure, man, like this is an abstract machine that is a little bit too abstract for me, because on the first line you're going to see the source of the language, and you're going to see the source of that language represents a value, a lambda, or an application, and you're going to tell me, dude, I've been to class as well, thank you very much. This is the lambda calculus, this is not a real language, we're not interested in your ranting around a real language. Okay, you want to see the CEK machine applied to a real language? Cool. This still fits in a slide. I have 15 rules instead of 5, but it's still 15 rules, right? I have a real language, I have a real syntax, I have an if, I have a let construct. Now, of course, you're going to tell me it's Lisp. Whether it's it is a minimalistic language. Yes, that's why we chose it as a first milestone. But it is a real language, it has real production code in the real world, and it is still very, very, very small. Now, what you're going to notice in the bits that are in here is that I'm dealing with 2 mutually recursive functions, one that has 7, one that has 8 instructions, and I'm firing one of those instructions one after the other. They're just literally a decoration of the source code. I'm working on the source code directly with a minimal amount of bookkeeping. And so that abstract machine model lets me define how several functional programming languages work. In many of the cases that you see on that slide, here's the fun part. The abstract machine is authoritative. What does that mean? It means if you write, the C++ was defined by the implementation of its compiler. So people came up with implementations, and then they said, what's C++? That's C++. And then researchers spent years, literally, and I know some of them personally, writing the specification of C++ retroactively from the compilers. And they had a lot of problems when there were mismatches, inevitably, between the specification and the actual compiler. A lot of functional programming languages were defined differently. They started with the abstract machine. And then they went to the implementation, and if the implementation does not match, does not do the same thing as the abstract machine does, then the implementation is wrong and the abstract machine is right, by definition. Now, that does not mean you can't define an abstract machine for, say, Python, which is not in this slide. It's actually relatively easy to define an abstract machine for Python, but it means that you have to convince other people that this is the real true Python. Because the real true Python is defined by whatever was on Guido's laptop at the time. That is what defines Python. Python has a big dictator for life. If Guido says you're wrong, you're wrong. I don't care how much work you've done. So you need to convince people that you're doing the same thing as Guido's laptop. But it is very much possible to define an abstract machine for Python. Cool. Now, what are the consequences of that, and why do you care? This kind of arithmetization is small and simple. Back in the days where we were only doing R1CS, now we are highly dependent on lookups, so the straight count doesn't really mean anything. But when we were doing only R1CS, we needed on the order of 12,000 constraints to make this. For your reference, this is half the size of the compression function of SHA-256. So you take SHA-256, you remove all the inits, all the padding, all that crap, you just focus on the compression function, you're down to 27,000 constraints, if my memory serves. I may be wrong, but this is within 10%, like it might be 24 or something, right? And I'm at half of that for defining an abstract machine that reduces a Lisp, a production Lisp at that. Right, and includes, other very cool things such as hash counting and using Poseidon and an interesting amount of stuff. So basically, this is small. This discipline lets you do proofs using a small amount of work, which is why we realized we were working on the basis of Nova with slightly different choices 5 months ago, and we were 55 times behind the competition in terms of performance. Now, don't get me wrong, I don't want to put that on Nova. We were also, how shall I say, not as clever as we could have been. But over the last 5 months, we have not only ported that from an R1CS-based implementation all the way to an AIR-based implementation. We're now 3 times ahead of the competition. And this is not just small fields. Now, don't get me wrong, there are people working in small fields in the room. I will recognize small fields go really, really fast. I spent several years trying to convince myself that you could do it without small fields, and I was humbly recognize small fields really go really, really fast. But we've had the time to port that and also modularize things so that the next port doesn't require that much work. So the next time that we're going to need to implement that on Stew with a different form of arithmetization, that's not going to take 5 months. And when we need to implement that on Binius, that's certainly not going to take 5 months because we will have ported that on Stew maybe at less than 6 weeks, something like that. The other thing is, when you want to formally verify things, and verify that your stuff is correct, the nice thing about having a paper that tells you here's the reference model for the reduction of JavaScript is, well, that's my specification. So now I just have to prove that the implementation matches the specification. I don't have to invent the specification. And at those sizes, we will be done so fast it's going to make your head spin. The only reason that we are not done at the moment, and God knows we have people in the team that would like to do formal verification, is that we keep innovating on the back end and how to do those proofs. So it's very fun in terms of company dynamics. You should join. Argument is a great company. There's constant fights between people that are like, stop touching it, I'm trying to verify it. And people are like, no, really, it could be better. So when I'm saying this can be faster, how much faster can this be? So we've done for you the cleanest possible and the most honest benchmarks. And this is so honest, I'm showing you a slide where I'm actually not faster. So here's the thing. The whole thing about abstract machines is that they go faster on the bookkeeping side of things. But if you have no bookkeeping, if your hardware representation has been made so as to do a special kind of computation really, 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 really fast, it turns out that saving on the bookkeeping doesn't save anything at all. So Fibonacci is the example of that. What that means is Fibonacci is putting stuff on your stack, adding them, putting more stuff on the stack, adding them, and so on and so forth. And that kind of permutation is already quite optimized. RISC-V will produce code that does that really fast with minimal amount of blah blah around the additions. And so it's really difficult to build SP1. So that you can interpret all of this, there's a blog post, you can read the blog post, have all of the detail, you can have all the code, you can reproduce all of this. I'm just giving you a very quick flavor. Sphinx is our slightly tuned variant of SP1. That is a fork that has minor differences. You have SP1 on the right. Lurk literally shares code with Sphinx. So we call into it as a library. We do not actually care about RISC-V at all. So of course we did not use a RISC-V prover, whether it's Sphinx or SP1, but there are some interesting functions and some interesting cryptography in there, including a fancy lookup argument. This is the cleanest differential benchmark you'll see ever. We're literally just implementing the thin abstract machine layer on top of a native prover and sharing everything in the prover, the good and the bad. We also have numbers for RISC-0 and Jolt. If you're interested, go see the blog post. So the pure Fibonacci of 50,000, of 10,000, not exactly faster, but when you're doing something, very esoteric, such as I'm going to take the vector of elements from 0 to 1,000, and I'm doing the Gauss summation, like I'm doing 0 plus 1 plus 2 plus 3 until 1,000. Turns out we're a little bit faster because there's a bit more bookkeeping involved. And when I say a bit faster, I mean a real bit faster. When you look at Fibonacci, there's one thing that has always frustrated us, which is that Fibonacci itself is computed in a messy way that doesn't actually even take advantage of the SIMD capabilities of the existing processors, if you think about it. So we thought, hey, or at least a genius among us, I'm actually not responsible for any of this personally, thought, hey, you know what? You can actually make Fibonacci go fast. And we have a fast Fibonacci implemented a matrix multiplication. 2x2 matrix multiplication, which will really actually make the stuff work. And there, well, there's a little bit of bookkeeping too, showing that RISC-V interpreted needs to figure out how to access the elements of that matrix. And in that bookkeeping, now stuff works a little bit faster. So that's pretty cool. But there's more. There's more because a few years ago, like I told you, this whole abstract machine stuff started in the 60s, but in the 80s, people started figuring out, well, all of those abstract machines function the same way. They take your big, gigantic program and they focus on a part of it and they contract it. And then they figure out which next part of the program they need to focus on. And they take that part and they contract it. And then they go all the way over there and they figure out which next part to look at it and focus it. And so what you were doing with your bookkeeping was that you had a stack, and that stack was represented either in a native stack or a continuation stack, but really you were spending a lot of time contracting things, focusing on the interesting bit, contracting things there, and then reconstructing the larger program so that you could have access to the other control term that you were looking at. And so they were using the full trait schema at the bottom of this figure. And then people figured out, well, there's this discipline of refocusing that actually in dotted lines allows you to go straight to the, if you can predict which part of the term you're looking at afterwards, that they allow you to go straight to which part you're going to contract. It turns out this is really difficult to figure out if you are reducing the term, but if you have reduced the term, you've run evaluation, not proving. You know everything that's going to happen, and so that refocusing thing, which is algorithmically very difficult to figure out, becomes trivial, and now you can basically do a proof plan exactly like the SQL query execution plans. And furthermore, this proof plan is actually a graph. I'm going to shut up because this is not my thing to explain. First, Chime has given a talk to it at the latest ZK Summit that was much better than anything I would say tonight. And there will be a paper to appear soon that I'm not an author of. But to give you an idea of some of the goodies that fall out of that, this is a super duper mega optimized Lurk program. I don't know if this is what you would write, but I can guarantee you this is top level, like 10x programmer Lurk program. We have memoization for free. That is, if we can call the shots in advance to what we're going to reduce, we're certainly not going to reduce the same thing twice. And then you're going to tell me, but how does memoization really matter? Surely, you know, we know that there are programs that need to be memoized, with the classical example being dynamic programming. Because we have all gone to interviews at large companies, right? Maybe not the academics in the room, but the academics in the room were training us for the interviews at the large companies anyway. So we've done to algorithmics, and you've had questions about dynamic programming, right? Dynamic programming is that thing that falls on every single interview, and you have just one way to go through it, it's memorization. And you're like, cool, so first it's a niche thing, and that dynamic programming thing is a thing that you will be requested to do on the interview. Typical thing, compute the longest common subsequence. Here we're benchmarking a longest common subsequence that is hand memorized in Rust. That is, that thing is actually doing dynamic programming techniques and actually builds a matrix with your intermediate results for the longest common subsequence. Those are the two bars on the right. We're actually optimizing the heck out of that, and then we're writing something relatively simple in Lurk by comparison, and we're getting something that automagically works quite a bit faster. Okay, so more in the upcoming paper. All of this is super cool, but this is the summary slide. This is exactly what we're doing with Lurk. The idea is, this is abstract machines. Abstract machines are tiny, and because they're tiny, they allow us to explore a very large design space. We had a prover based on Nova called Arecibo. We have a prover that was based on SP1 that we call Sphinx. Our theme is that we are naming them after observatories. We like looking at the stars, and we're all romantics. But we will also explore languages. We've been on Lisp so far because we're fixing the backends. We're now embarking in an adventure to support Camel. And there will be more things in the future if we have the occasion to play with that very nice project. Abstract machines are a framework that let you do that, and that let you do that for relatively free, because again, emulating hardware, very important if you're actually going to run on hardware, not so important if you're doing math. And that just diminishes the footprint of how much effort we have to put into every bit that we're doing. So that's Lurk.